it's treated by compilers as if it were a local variable. So in this case here, the by value parameter could be constructed in the return value location. If instead you apply move to it, trying to help the compiler, then the compiler cannot generate that same code. Here we'd actually have to perform a move operation. So the general rule is compilers understand more about returning local variables and by value parameters than you do, and they don't need any help. Which means that if we have some identifier ID of some type T, then if we have an R value reference parameter, you want to say I want to move. If it's a universal reference parameter, you want to say forward. And if it's a non-reference, you just want to return the value of the parameter. So use move on R value references, use forward on universal references, and to be safe, don't use them anyplace else. So the guideline is to use move with R value reference parameters and universal references to get forward. What I want to do now is talk about the actual technical underpinning that makes everything work. And that is to understand reference collapsing. We will start with the observation, you cannot declare a reference to a reference. If you try to say widget ref, this will not compile. You are not permitted to declare references to references. However, I can have a reference to a reference arise during type deduction. As an example, here's a universal reference. Early this morning, I told you that if you pass in an L value, the type that is deduced is going to be an L value reference. I said if you pass an R value, you get a non-reference. Notice the asymmetry. L values are signified by an L value reference. R values are signified by a non-reference. If I call f of w, the type T will be deduced to be widget ref because w is an L value. If I do f of standard move of w, that's an R value, the type will just be widget. This is the type deduction rule for universal references. It's essentially one special rule, which is L values are always deduced to be an L value reference type. So here's the function f that takes a universal reference. I now call f of w. The compiler says, okay, this is an L value reference. The type T is therefore deduced to be widget ref. So we take T, which is widget ref, and we substitute it in right here, and we end up with widget ref, ref. Notice, this refers to T, but T has a reference of its own. We have a reference to a reference. You can't write this, but it can arise during template instantiation. Anytime you have a reference to a reference that arises like this, we have a process known as reference collapsing that kicks in. There are two reference types, L value and R value. There are therefore four possible combinations. If I have an L value reference with L value reference, I get an L value reference. L value to R value is L value, R value to L value is L value, R value, R value, R value. In other words, if either reference is an L value reference, the result is an L value reference. And if both of them are R value references, the result is an R value reference. Stefan Lawade, he says L value references are infectious. Earlier I told you that the idea behind a universal reference was a lie. Now I can tell you the truth. Here's the truth. A universal reference is an R value reference in a reference collapsing context. Technically, tref is always an R value reference. Technically. It's just not helpful to think about it that way in my I've already mentioned that function template parameters are the most common context where reference collapsing occurs. There are 4 reference collapsing contexts. Most common by far, templates. Universal reference. Actually, now we know it's an R-value reference. I call it with an L value. When I call it with an L value, I end up with f of widget ref. I get an R value reference to an L value reference. After reference collapsing, that gives me f of widget ref, which is why what I told you before is if you call a function with a universal reference and you pass it an L value, this becomes an L value reference. If I call it with an R value, then remember the type will just be that it's to be widget. There's no reference collapsing necessary. I call f of widget ref. Auto ref is another reference collapsing context. This is a universal reference. So the type deduced for W will be widget ref because this is an L value. I'll therefore have auto ref becomes widget ref, which after reference collapsing becomes widget ref. Auto ref here, this is an R value. The type that is deduced therefore is just widget, so the type is widget ref. There are 4 reference collapsing contexts. Number 1, templates, by far the most common. Number 2, auto ref, much less common. Number 3, type defs. I've got a widget class here, type def, tref, L value ref type. Seems like a pretty good name. So if I now say I've got a type def for widget of int, L value ref type ref, R value reference to, let's see, widget L value reference type. This looks like an R value reference. But widget of int, L value ref type is an L value reference, which means we have an R value reference to an L value reference. After collapsing, they will become an L value reference, which means the type is just int ref. Which means that this name, which was never very good to begin with, is even worse now that we realize it isn't even an R value reference. So, if during template expansion, type def expansion, you end up with references to references, reference collapsing occurs. The final of the 4 contexts where reference collapsing occurs is in decal type expressions. I already mentioned that for decal type, if I say decal type of a name, I get the declared type of the name. Decal type of an L value expression is going to be an L value reference. And decal type of a R value expression will just be a non-reference type. So in this case here, decal type of W is just widget. So we get widget ref. This is an R value reference. So R1's type is widget ref. Remember that if you put parentheses around it, it goes from being a name to an expression. So decal type of paren, W paren, that kicks in with this rule here. The result of this is widget ref, which is then combined with this. If I now have an R value reference and an L value reference, they collapse down to an L value reference. And R2 is therefore a widget L value reference. But I'm trying to initialize it with an R value, and that won't compile because you can't initialize an L value reference with an R value. The only thing you need to remember from this entire slide is decal type is a reference collapsing context. It's the only thing you need to remember. So the truth of the matter is that reference collapsing is what's going on. If you understand the rules for reference collapsing, you understand everything about how C++ R value references work. You don't need any more. You can reason everything from first principles. And I know some people who believe that is honestly the best way to do it. And I think those people are crazy. There are two important reasons, I think, to talk about universal references, what the committee now seems to want to call forwarding references. The first one is code comprehension. So it's important to understand, if you read type ref, if you read this in some source code, you really need to understand whether that can only bind to R values, in which case it should always do moves, or whether it can bind to L values or R values. So you need to distinguish between those two. And I also believe it's very important when communicating with your fellow developers. If you just say, well, I use an R value reference, but it's not clear what that means, that does not help. I think it's important to be able to say, this parameter is an R value reference, and the person talking to you will understand only R values can bind to that. On the other hand, if you say, well, I used a universal reference, the person you're talking to will understand, that means maybe L values will bind and maybe R values will bind. And they'll behave differently. This acts like a universal reference. It doesn't act like an R value reference. This acts like a universal reference. It doesn't act like an R value reference. Because they don't act like R value references, I don't think we should use the same name for them. The guideline, therefore, is to understand reference collapse. This takes us out of the deep, dark, detailed woods of references and of R value references and loop semantics. Any questions about anything to do with that stuff? It's going to be easier from now on.
The previous slide on the for, would you actually, if I don't want to look, what's the signature of the factory? Should I just use ultra-ref? If I kind of don't care what the factory returns.
Okay, so the question is, let's suppose I'm calling a factory. I don't really care what it returns. Maybe it returns an L value, maybe it returns an R value. I don't care. All I know is I want to refer to every element that is returned. And then the answer is yes, you can use auto-ref for that.
Okay.
So it turns out that in C++ 17, they've actually, or they're going to introduce an abbreviated shorthand which will cover the case for you. And the reason they're doing that is because they don't want you to have to write auto-ref. But if you actually look at the specification is this is exactly what it does.
Right.
Earlier I showed you the range-based for loop. It also used auto-ref because it doesn't care about whether the initializing expression yields an L value or an R value. Okay?
The shorthand that you mentioned, yes. Can I look it up from somewhere? Not so important. If you
send me some email. I'll track down the. I can't remember what it's called, but it's yet another form of range-based for loop.
Okay. Thank you.
As far as I know, actually it might be implemented in Microsoft's compiler now that I think. In my experience, when people come to C++ 11, they hear about move semantics, they hear about how wonderful things are, how cheap things are, and they go, this is just great. And what you find out is that some of the copies in C++ 03 become move operations, which means they're usually cheaper. There's a ton of support in the standard library. Moving containers is actually vastly faster than copying them. It's a really important optimization. My concern is that sometimes people think this is great, I never have to worry about how much copies cost anymore. Because everything's just going to be moved all the time. And this is bad. So what I want to do is remind you of the restrictions on some move operations. The first thing is, move operations are not supported by all types. All the types created before 2011 lack move operations, basically. And a whole lot of types since then lack move operations. There is one exception. Under some conditions, compilers will automatically generate move operations for you. But that's only for types that don't have copy constructors, don't have copying functions, constructors or assignment operators, don't have move operations, and don't declare destructors. So the universe of types that get compiler-generated move operations is pretty small. The second thing to know about the move operations is that they only support, they get limited support by some types. If you move a vector, it's very, very fast. If you move a list, it's very, very fast. If you move almost any container, it's very, very fast. One of the containers in C++11 is standard array. Standard array doesn't use heap memory. It's actually a regular global or stack-based array that has an STL interface on top of it. It can't be moved quickly. If you do a move on an array, it does support move operations. It will move every element one by one, but it still runs in linear time. Moving an array is much slower than moving a vector. So it is faster than copying, but it's not fast. So that's an example of a standard type where maybe it's fast, but probably it's not. Even when moving is supported, it's not always faster than copying. Small strings use what is known as the small string optimization. This is quite commonly implemented. Microsoft implements it. I'm pretty sure Clang does. GCC sort of does. When you have a small string optimization and you have a capacity of typically either 7 or 15 characters, which is not very many. That's on a 32-bit machine, that's 4 machine words. We're not talking a lot of memory. But under those conditions, they can't be moved more quickly than they're copied. It's the same speed. Moving's not slower, it's just not faster. It's worth pointing out that moving is generally restricted only to R values. So copying L values generally requires copying. And interestingly enough, the move operations aren't always used. Let us imagine I have a string that has the value, this string has 29 characters. Assuming I've counted correctly, that's a true statement. Here's a widget class that has a data member of type string, and whenever you create one, it simply takes this string value and copies it into the data member. So basically, a widget is nothing but a wrapper around a string. That's all it is. It's a wrapper around a string. I now have a vector of widgets. So what I want to do is just a little bit of benchmarking. And what I'm going to do is I'm going to choose for some number n, I'm just going to do n pushbacks of w, n pushbacks of a widget into the vector. So I'm simply going to create a vector and keep adding new widgets to it. Now remember, a widget is basically just a string. Pushback has an exception safety guarantee. In particular, it has the strong exception safety guarantee. The strong exception safety guarantee says if you call pushback and an exception occurs, the vector is unmodified. Same guarantee in C++11. It has to be the same guarantee in C++11. If we had a different guarantee in C++11, then C++98 code could have been broken. So it's important to have the same guarantee. Let's suppose this is my original vector. It's full. There's no empty space, and I do a pushback on it. Well, because there's no empty space, I have to allocate more memory. So what I do is I allocate some more memory, except that now all the elements that are in this memory have to somehow find themselves in this memory. In C++98, the only thing we could do was copy them. That was no problem. Copy, 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 copy. If in the middle of this copying an exception was thrown, that was okay. The original vector had not been changed in any way. Strong exception safety guarantee. In C++11, the logical thing to do is to say, why are we copying all these elements? Let's move them instead. So let's assume that we give our widget class a move operation. Move, 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 move. These elements words have been modified by being moved from, and there's no guarantee we can move things back, that might throw an exception too. As a result, pushback on vector and several other functions can only perform a move if they know that the move operations are guaranteed to not throw exceptions. So for those classes, it's not enough to have move operations. You have to have move operations which guarantee they won't throw exceptions. This is a couple of benchmarks I did. This is from, I think, about a year ago. I don't remember. And this is with 10,000 elements in the vector. You can see the same data. This is 1,000 elements. That's 100 elements. But we'll look just at this one. Two compilers. This is Visual C++ 12. This is GCC 4.8.1. Those were both current at the time that I did my testing. And so this is how much time it takes for doing 10,000 insertions with copy operations. And then I said, if you have a move operation, it's either declared no except or it's not declared no except. These are both the move operations. What I want you to notice right away is copying much slower than moving. Copying much slower than moving. Now, what you may also notice is that this is doing a move where it could throw an exception. This is doing a move where it can't throw an exception. Notice that they're the same length. That's completely contradictory to what I told you. What I told you was, if the move operation might throw, it has to do a copy instead. And that's true. There's simply a shortcoming in the Microsoft implementation. Microsoft's implementation says, we're going to assume it never throws. So this bar here should be out to here. Just like it is with GCC. This is the GCC data. Now, the first thing you're probably doing is you're going, whoa, that is one big bar. These are little tiny bars. I do not want you to come to the conclusion that GCC has a much better implementation than Microsoft's does. Because Microsoft's implementation is non-conforming. It assumes that the move operations don't throw. GCC's implementation is also non-conforming. It uses reference counting on strings, which is not permitted in C++ 11. So they're both wrong. But what GCC does do correctly is pay attention to whether the function is declared that it might throw exceptions. This is how much time it takes to copy things with no move operations. If I have a move operation that is not declared no except, which means it could throw an exception, notice it runs at basically the same speed. If I then take the move operation and declare it no except, notice it runs noticeably faster. Yes?
How does STD unexpected fit into this picture?
So the question is, how does STD unexpected fit into the picture? And the answer is, it is independent of STD unexpected. So unexpected is a function that gets called if an exception gets thrown that is not in the exception specification list.
If you specify that nothing is thrown, isn't that also thrown when something is?
For our purposes here, what we are interested in is what happens if I have move operations and they don't throw, and they are declared either to not throw or they're not declared to not throw. So all we care about for purposes of this discussion is what is the impact of declaring that they will not throw. If they actually do throw an exception, that's a whole separate issue. Generally speaking, you want to write your move operations so that they cannot throw. And if you can write efficient move operations, usually there is a natural implementation where they will not throw. Okay? In these examples here, no exceptions were ever thrown. So I was simply experimenting with the difference between declaring them to not throw and not declaring them to not throw. And what actually happens is, in both cases, not in both cases, What actually happens is, if you have a move operation and it is not guaranteed to not throw, let me rephrase that. If you have a move operation and it might throw, then, going back to, then it won't even be called. If you have a move operation that might throw, it won't even be called, you'll do copies instead. Which means if you have a move operation in your class, it still might not be called. In particular, under certain conditions, inside vector, inside some other STL containers, if you have a move operation and it isn't declared that it won't throw, then your function might not be called. You might get a copy instead. And there's actually a construct in the library which allows library implementers to find out whether it can throw or not. But what I want to point out is, regardless of your compiler, copy takes longer than moving. Copy takes longer than moving. Now, one of the lessons here you want to remember is try to have your move operations not throw. But for purposes of our discussion, what I'm trying to get across is, even if you have move operations, they may not be called under some conditions. And in particular, they may not be called if they could throw an exception and you're in functions like pushback. But pushback is not the only function like that. There are several vector functions. Resize is another one. I think insert might be another one, but I'm not certain about that. Depends on which exception safety guarantee they offer in C++ 98. And what I want you to notice too is here in the lower right-hand corner, this is a vector of 100 elements. That is not very big. 100 elements is very small. And notice that you still see a noticeable difference here. So this is the kind of thing that is important even on fairly small vectors. So move semantics, which means using move operations instead of copy operations, does not help you if the source is an L value, if the type offers no move support, if moving is no cheaper than copying, and if move is unusable, for example, because it's not declared no except. But the guideline is to assume that the move operations are not present. Now, if for some expression in your source code, you know the types involved, and you know that they support cheap move operations, and you know that the expressions use those move operations, you don't have to make any assumptions at all. If you know all the types involved, if you know all the expressions involved, the expression will employ the cheap move operations. This is not up to the compiler. We're not talking about compiler optimizations. Whether to form a move or a copy is part of overload resolution. Compilers have no choice in the matter. They have to do the move when the conditions are fulfilled. But if you don't know the types involved, or you don't know what the expressions are doing, most commonly because you're writing a template, then you have to assume the worst. So the guideline is to assume that move operations are not present, not cheap, and not used. But the broader message I'm trying to get across here is that even in a world that has move operations enabled, you still have to be careful to not create too many objects, not copy too many objects. It doesn't make all your performance issues go away. It makes them easier, but it doesn't mean you can stop worrying about it. Any questions about the existence of move operations? Any questions about anything to do with move semantics? All right, then I'm going to switch gears completely. We're now moving to Lambda functions. I only have one day, so we're kind of jumping around a little bit. I was trying to come up with things that I thought would be most useful. I spent as much time as I did on move semantics because in my experience, it's one of the more difficult topics to understand. And I also think that it's important to have a good understanding of it as professional developers. So this is about lambdas. So You want to avoid default capture modes, which I feel kind of badly delivering this message because default capture modes are one of the most convenient things about lambdas. They've got nice syntax for it. The problem is that default by reference capture can lead to dangling references, which should seem fairly obvious. Default by value capture is a little more insidious. It seems like it should prevent dangling references, but it doesn't. And it seems like it should guarantee that your closures will be completely self-contained, so you don't have to worry about lifetime issues, but it doesn't. So they seem to offer things that they don't. I mentioned earlier that standard function is a generalization of a function pointer. It can refer to anything, in this case, if it takes an int and returns a bool. But let us assume I'm going to have a whole bunch of functions which I'm going to be using for filtering things. So I'm actually going to have a vector of standard functions, and I'm going to call that type vector of these things is a filter container, and then I'm going to have a collection of filters. So the idea is I have a vector, conceptually I have a vector of functions, but they're anything that can act like functions. And I'm going to use them for filtering things. So they're all going to return true or false. So here is a function, add divisor filter. So I compute some calculation number 1, I compute some calculation number 2. I then figure out what my divisor is. I call compute divisor of calc 1 and calc 2. And now what I do is I add to the filters container, that's this one here. I add to the filters container, rather than directly adding a standard function object, I'm actually going to add a lambda. And as a result, instead of calling pushback, I'm going to call in placeback. It will be more efficient to call in placeback. So in this case, I'm just going to say, given a particular value, I want to return whether the value is evenly divisible by the divisor. Notice that I am using a default by reference capture. Divisor is a local variable. We will therefore have a reference to divisor inside the lambda, which will then be put inside filters. At the end of this in place back statement, we will exit add divisor filter. When we exit add divisor filter, divisor will be removed from the stack frame, and we will have a dangling reference inside one of the filters here, which means it's going to blow up on us at some point later, probably, possibly much later in the program. Any questions about how this is a dangling reference, essentially at the point where it's created? Now, to be fair, if you expressly listed it this way, this says I want to capture divisor by reference. You can still dangle. This dangles just as much as the previous one does. The difference is, if I go back one slide, this is sort of a general, this syntax sort of is a general way of saying, by the way, something might dangle. You better check things. It's a general reminder. Whereas this says, okay, divisor might dangle. You need to check divisor. By listing the name expressly, it becomes easier for people to verify that we don't have a problem, or in this case, to confirm that we do have a problem. So that's the problem with default by reference capture. Technically, if I'm going to use a lambda at exactly one point in the program, I'm not going to save it, I'm okay. So this is the same code I had before. Basically, do some computations, get my divisor. Now, what I might do inside work with container here is I might say, okay, from the beginning of the container to the end of the container, all of is a new STL algorithm for C++ 11. It does exactly what you think it does. It checks to make sure that a predicate returns true for every element of a range. So what I want to know is, does every element of this container satisfy this predicate here? Notice the default by reference capture. In this particular case, there's no problem. This lambda will be created here. It will refer to divisor, but this lambda will only exist until the end of this statement. And this statement here, divisor will live at least that long. There's nothing unsafe in terms of lifetime with what I'm showing you here. The problem is, let's suppose you look at this code and you go, you know, that filter does exactly what I want. So what I want to do is add the lambda to filters. If I were to take this code here and do a copy and paste and add it to the filters function, that would take us back to the situation where I had a dangling pointer. My belief is that explicit captures are simply better software engineering. Having default by reference captures in your lambdas, in my view, is exactly the same as declaring all your variables in global scope and referring to the ones that you want, which we decided in the 1960s was a bad idea. So that's my argument against by reference capture by default. Well, in that case, you might think, okay, by reference is bad, but I can use by value instead. Well, the thing is, it doesn't preclude dangling, because captured pointers can still dangle. If you capture a pointer by value, you copy the bits of the pointer. But obviously, if the pointer dangles, then the bits of the pointer are going to dangle as well. Which means the default by value capture can give you a false sense of security. Sometimes I meet people and they go, it's not a problem for me. I only use smart pointers. I only use shared pointer. I only use unique pointer. I do not use those dirty, nasty built-in pointers. And I always say, yes, you do. Everybody does. Everybody uses built-in pointers, even if you don't want to. Here's a class widget. Here's a function to add a filter. Here is a data member divisor. So here's a widget add filter. So I say, great, I'm going to do it in place back. Same code I had before, but now I am so cool. I am doing it by value. I mean, this looks about as safe as you can possibly get. It looks safe, it looks self-contained. It is neither one of those things. This does not capture divisor. Code compiles, code runs, might work. Only non-static local variables can be captured, and divisor isn't local. Let me go back a slide. There is no divisor in this function. There is only a divisor here. This is a data member of the class. When I refer to divisor right here, when I refer to divisor, I am really referring to this arrow divisor. There is a local variable. Let me go back one slide. There is a local variable here. You can't see it. But there's a local variable in this function. The local variable is this. What this is capturing is the this pointer. And this is why everybody uses built-in pointers. It's because every member function has a this pointer. Not a smart pointer, it's a dumb pointer. From a capture perspective, what compilers are really doing is they're saying, I'm going to have a current object pointer called this. That's what I'm going to capture, and I use current object pointer here. That's essentially what happens, is I make my own copy of the this pointer, and that's what I put into my closure. Well, now that we understand that we have a copy of the current object in the closure, all we have to do is figure out how can this possibly fail. I have an example right here. I call make unique. Make unique is a C++ 14 function. It causes an object to be dynamically allocated on the heap, and you're given a unique pointer to it. So in this case, I create a widget on the heap. I get a unique pointer to it. PW is a unique pointer to a widget. The widget's on the heap. Now I call it add filter again. This is essentially how add filter behaves. So what happens inside add filter is I create this lambda and I put it in the filters container. Remember, filters in place back. I take this lambda, put it in the filters container, and I know that this particular lambda has a pointer to the current object. The current object, going forward one slide, the current object is the widget that's on the heap. At the end of this function, the local variable PW has its destructor called. Because it is a unique pointer, it will automatically delete what it points to. Which means that the object is no longer on the heap, it's been destroyed. And that means, going back one slide, that the filters container now holds a closure which has a dangling pointer to a widget because the widget doesn't exist anymore. Any questions about how this yields a dangling raw pointer in the filters? If you really want to make this self-contained, then what you can do is you can actually say, okay, I'm going to copy the divisor, the data member, into the local thing divisor copy. I can now capture divisor copy by name, use divisor copy here. This is self-contained. It's no longer dependent on a widget, it's only dependent on the copy of divisor. Now, you could use default by value capture, but that's what got you into trouble in the first place. But let me change the example a little bit. I'm just going to change it one tiny little bit. I just made a few things static. That's all. Just made a few things static. So divisor is now static. Notice the default by value capture. Divisor is a local variable. I'm using divisor here. There's no member functions going on here. This is pretty straightforward. And then I'm going to count how many times I call add divisor filter. There it is, plus plus divisor. The only problem with this code, this doesn't capture anything. This has no effect at all. Instead, what's going to happen here is every time divisor gets changed, it's going to be reflected inside this filter here. And the reason for that is because only non-static locals can be captured. You can't capture things that are static. Now, this code will compile, but this does not capture anything at all. This lambda is going to refer to this chunk of memory directly. It's not making a copy of it. Which means that default by value does not imply that a closure is self-contained. Instead, if you explicitly list the variables you want to capture, this is where things become interesting. Compilers reject uncapturable variables. So for example, if you try to capture a class data member, the code will be rejected. If you try to capture something of static storage duration, like a local static, the code will be rejected. If you try to capture a global variable, the code will be rejected.
Why?
So the question is why? Why will it be rejected? It will be rejected because the language rule is you can only capture non-static local variables. And I think the thinking is if you wanted to capture one of these other things, you'd copy it into a local variable and then you'd capture that. From my perspective, I consider it a feature that will actually check to make sure that the things that you list are things that you can actually capture. It reduces the risk of dangling captures. I'm not going to say it eliminates them. You can still capture pointers and they can dangle. And it reduces the false sense of security regarding closures being self-contained. And this is why the guideline is to avoid default capture modes. Okay, there's only one more guideline that we're going to talk about, but I know there's a couple of people who need to leave soon. So let's take our 10-minute break now, and then we'll come back. We'll cover the one more guideline. I'll have a couple more things to say.